Okay, so here we're going to look at hypothesis tests for proportion. The setup is very similar to hypothesis tests for mu. To find the test statistic, you find the difference of the sample statistic and the hypothesized population parameter. That result is divided by the standard deviation of the sampling distribution. The ones we've done in the past are for the mean, mu. If sigma was known, we use the z. Sigma unknown, we use the t. When I say up here the difference of the sample statistic and the hypothesized population parameter, that probably sounds really confusing, but that's just saying x bar, the sample statistic, minus the hypothesized population parameter, which is mu. So x bar minus mu is in the numerator, and then you divide that by the standard deviation of the sampling distribution. So when we're looking at means, that's sigma over the square root of n, or s over the square root of n. For us, using proportions now, the difference in the sample statistic, that's p hat, and the hypothesized population parameter, that's p. So you subtract those, just like x bar minus mu, same idea here, p hat minus p, divided by the standard deviation of our sampling distribution, which is the square root of pq over n. Now notice when we're doing this, that we're using pq because now we have a value for p. Okay, we have a hypothesized value for p, so now we can use p and q rather than p hat q hat underneath the square root. Like we did in our confidence intervals, we use p hat and q hat. Now because we have p, we're going to use p and q. Okay, so in number 1, we have a claim that a population proportion is less than 0.37. So somebody's making a claim that some proportion is less than 0.37. So I give you these statistics. P hat is 0.32, your sample size was 320, and alpha is 0.05. So with no context to the question, let's test this claim. Okay, so our hypotheses were that p equals 0.37 for the null, and the alternative would be our claim that p is less than 0.37. Okay, so on a z-axis for our rejection region for HO, if alpha is 0.05, a left tail test because of the less than 0.37, so a left tail test, that critical number for z star was negative 1.645. So now we collected our data. We got a p hat value of 0.32. So now we need to calculate the test statistic. Okay, using up here. Okay, so plug your numbers in. And the biggest place that people make a mistake on this, we don't put p hat and q hat here. We're putting p and q because we have our hypothesized value of p right here. Okay, so do not put 0.32 here instead of 0.37. Okay, that's the biggest thing that people miss on these. Okay, so when you do that arithmetic, you end up getting negative 1.85. So negative 1.85, if we look at that on our rejection region, that test statistic is going to be out here to the left. So our decision, just like before, we would reject HO, which means there's enough evidence to support the claim that p is less than 0.37. Okay, on the next page, another example. A college claims that more than 80% of their graduates are employed within 6 months of their graduation. The president was concerned whether they should advertise this claim in their college brochures. In a random sample of 300 of the graduates, 250 said they were employed within 6 months of their graduation. Test the college's claim with alpha equals 0.10. Okay, so again, when we look at this, we need to recognize that the claim is that more than 80% are employed. Okay, so 80% is a proportion. Okay, so the college is claiming that P is greater than 0.8. Okay, so that's your alternative because of the greater than. So your null is that P equals 0.8. So this is a right tail test because P is greater than 0.8 was your alternative. So right tail test. Alpha was 0.1. The Z star value that goes with 10% to its right is positive 1.28. So if your test statistic ends up being larger than 1.28, that means that that assumption that P equals 0.80 was right in the center was a faulty assumption. Okay, so what happened in our sample? 250 out of 300 said they were employed, minus the population proportion, which is 0.8, comes from our null hypothesis, and then divide by the square root of 0.8 times 0.2 over 300. That gives us a Z value, a test statistic of 1.44, which we can see is a little bit to the right of 1.28. So that means that if 0.8 really was the population proportion, then getting that sample proportion of 250 out of 300 would have been unusual, or more unusual than we were willing to accept. So our decision is to reject HO, which means, again, in this case, there's enough evidence to support the claim that P is greater than 0.8.